Hello, everyone, and welcome into this special recording for ME2002. It's Monday, February 1st, and I'm recording here a video about cylindrical components and kinematic problems. I've had a couple of questions on homework number 6 about problems number 4 and 5, and I thought maybe I'd record this video to help sort of explain some of these homework problems and these cylindrical coordinates, since we didn't get a chance in lecture since I was gone on Thursday to really talk about them. So let's dive in and look at your homework problems and maybe talk about some of the things that are going on quickly. So here I've copied over to the writing pad homework problems number 4 and number 5. I guess the numbers kind of got lost here, but this is number 4 and this is number 5 down here. We'll get to in a second. And we have these cylindrical coordinate problems. And specifically, I want to remind you what the coordinate system for cylindrical problems looks like. So generally we have some coordinate system that's like an r theta coordinate system. It might be depicted in this way. We've got some particle that exists out here in space. It's point P, and it's located away from an origin at O with some position vector r. Now, coming off of this particular particle are your unit vectors, where the first unit vector that we sort of first defined is this unit vector in the radial direction, E hat r. And the second unit vector that we defined is 90 degrees counterclockwise from that, which is E hat theta. Now, the lecture video goes over all the gory details about how we define velocity and acceleration. But in the end, we ultimately want to get to a point for each one of these problems if we're looking at calculating velocity and acceleration, where we can calculate velocity using something that looks like this. R dot E hat r plus r theta dot E hat theta. And you want to get to a point where you can calculate acceleration with your typical acceleration form for cylindrical coordinates, which is r double dot minus r theta dot squared E hat r plus your transverse component, which is r theta double dot plus 2 r dot theta dot E hat theta. If you are a little bit shaky on where each one of these comes from, I'd encourage you to go back and watch the lecture video that I did last Wednesday for what would have been last Thursday's lecture on how we sort of derive these velocity and acceleration expressions. But the point is, when we're looking at homework problems that deal with cylindrical coordinates, like number 4 and number 5 that you have on your assignment, you ultimately want to get to somewhere where you have these terms, like r dot, theta dot, r double dot, theta double dot, r, and sometimes theta, depending. So the point is you want to get to a situation where you have r dot, r double dot, theta, theta dot, and theta double dot. So you want r dot, r double dot, theta, theta dot, and theta double dot, usually as a function of time. Though that's not always a requirement. Okay. So there's two types of problems that you'll typically see when you're looking at these cylindrical coordinate kinematic problems. And the first is like problem number 4. And in this particular situation, we have theta and the position r both as a function of time. So in this particular situation, we have theta as a function of time, and we have position as a function of time. All right. So to get things like theta dot, theta double dot, and r double dot, all you do is just take these expressions that are given and differentiate them with respect to time. So in this particular situation, it's rather trivial to get to, let's say, theta dot as a function of time. Sorry, there's some like fire alarms going on in the background here in my apartment. I don't know what's happening, but hopefully that stops soon. Maybe it's not even coming through the mic anyways. But the idea here is that to go from theta as a function of time and r as a function of time to theta dot and r dot as a function of time, we just want to take the time derivative. And that's pretty straightforward because we already have our positional or angular position and radial position as a function of time. And we can even go one more step further, take another derivative to get what would be theta double dot as a function of time and r double dot as a function of time. So for problem number 4, these are pretty straightforward. You'll have to figure out a time derivative for t to the 1/2 or 1.5 power, which should be rather simplistic if you've done some calculus. And here we have a t to the 3rd, so this is a typical kind of polynomial type derivative, so that should be pretty straightforward. Okay. Once you have all these pieces of information, it then just becomes kind of a plug and chug. Specifically for this problem, you're interested in a time of 1.5 seconds. So keep t as a variable as you're taking all your derivatives, and then at 1.5 seconds, figure out what all these particular variables are. That's sort of problem type number 1. That one's pretty straightforward and pretty straight ahead, where you have individual positions as a function of time. You just take derivatives and go about your business. The more difficult type problem is problem number 5, similar to problem number 5. And problem number 5, you have a little bit of complication here because you're not given the position and the angular location as a function of time. Instead, they are functions of each other. So here we have something like the position r as a function of theta. So typically they're given independently with a parameterized variable, which is time. But here we have a differential equation where they're actually given as functions of each other. And so to deal with this, we have to have a little bit of a different tact, a little bit of a different strategy. And that particular strategy is going to leverage sort of the chain rule and some calculus techniques that maybe you haven't used in a while. So the idea here is that you have, let's say, r as a function of theta, which might be something like 0.4 theta. Okay. And I give you a hint in this particular problem that in order to get something like r dot, r double dot, and theta dot, theta double dot for these problems, you just want to differentiate this particular relationship directly as a function of time. What that's going to afford you is on the left-hand side, you'll just get r dot. On the right-hand side, you'll just get theta dot. So let's see what that might actually look like. So if we just differentiate this whole thing directly, and I think about this particular derivative, well, there's a couple of ways that we can go about it, but I think the easiest way to understand it is to just understand that the time derivative of this is r dot on the left-hand side. It's the time derivative of the left. And the right-hand side will be just something like 0.4 times d theta dt, which would just be theta dot. Right? So here now we have a relationship between how fast this thing is moving velocity-wise away from the origin, and how fast this coordinate system is rotating. Remember, this is your angle velocity theta dot. And you can even go one more derivative here, where you have something like r double dot is equal to 0.4 theta double dot. It's just direct time derivatives. Now, this is pretty simplistic, where you just have linear relationship between one and the other. And sometimes these relationships can be a little bit more complicated, like what happens if you have something like r as a function of theta is equal to, e to the theta. That becomes a little bit more complicated when you're trying to take the time derivative of this, because you don't have a direct, theta dot on this right-hand side. So this will be all I'll say about the homework, I guess, at this point. But I do want to do one example problem that has a little bit more relationship-driven issues, where we're looking at something like what happens when your position vector is a function of theta, and it's not so easy to see how the time derivatives sort of work out. Okay, so I'm going to bring in a practice problem here, and we're going to talk our way through it. So here we have a particular example problem that I've sort of cooked up from your textbook. So here we have a cylindrical coordinate type problem, and in this particular situation, it's very similar to the problem type 2 that I explained previously, where here we see that our position r is a function of the angular position theta. So this is kind of problem type 2, where your position is a direct relationship with your angular value theta. Okay, so we're asked in this particular problem to determine the velocity vector of the peg p at this instant and the acceleration vector at this particular instant, when we have a variety of information about this piece known. So, for instance, we know that at theta is pi on 4, the link has an angular velocity of 2 radians per second and an angular acceleration of 4 radians per second squared. So we're going to take that information and utilize it to do everything that we see in the bullet list here, which is like peg's relationship to O, the unit vectors, E at r, E at theta, velocity vector, and acceleration vector. We're also asked to create a sketch. So if you want, you can sort of pause the video right now to sort of copy down the problem entirely, and I'll give you a second to do that here, and then I'll just get on with the solution. Okay, hopefully you've had a chance to copy the problem down. I'm going to go ahead and put this directly into my writing pad here. Whoa, baby. Never know what you're going to get when you just copy paste these large things in here. Always a mystery. Hopefully it'll be a little more nice this time. Okay, still not nice, but I think I can fix this. All right, maybe not. Sorry, you can probably fast forward about, 15 seconds and I'll have this figured out. Okay, here's our picture. We're given that position r is a function of theta, and also we know in the problem, I'll just copy this down, theta is pi on 4 at this particular instant. Theta dot, which is the angular velocity, is 2 radians per second. And theta double dot, which is the angular acceleration, 4 radians per second squared. Okay. So let's work through the solution, and I'll just kind of go through it fully, where we're looking at calculating the velocity and acceleration vectors and then sketching everything associated. Okay, so we're going to use our sort of cylindrical coordinates here, and we know that the velocity is something like r dot e hat r plus r theta dot e hat theta. So that's where we're going to go for the velocity. And we also know that the acceleration is something like r double dot minus here r theta dot squared e hat r plus here we have a 2r dot theta dot, our Coriolis term, plus r theta double dot in the transverse direction e hat theta. Okay, so more or less what we need is we need r dot, we need r double dot at this particular moment in time, because we already have information associated up here with, let's say, theta, theta dot, and theta double dot. Okay, so let's go about this and give this a go. So here we need, I'll say, given that this position as a function of theta is e to the theta, what is r dot and r double dot? All right. Well, we'll just go with our typical time derivatives, right? So remember that r dot is just dr dt, but I have that this r here is a function of theta. So let's plug that in and see what happens. So this is the time derivative of e to the theta. And this is where things get a little sticky. How do I sort of deal with this? And the way that we deal with this is chain rule. You'll remember in the derivation for, let's say, the derivative of the unit vectors, we used a lot of chain rule to sort of help us through some of these strange derivatives. So let's go ahead and sort of rewrite that with that idea. So here we have r dot, which is the time derivative here of this function e to the theta. And we might think about rewriting this with a chain rule using some information that we can sort of already understand. And that might be, here we'll do the derivative of e to the theta not with respect to time, but with respect to theta. And then we'll tack onto that a d theta dt. So these two things are more or less equivalent and now are written in terms of things that we can sort of understand. So given this information, all right, well, the derivative of e to the theta with respect to theta, that should be something you easily identify as just the exponential theta. You know, it's one of those special derivatives. You get back the exact same thing when you take the derivative of that guy with respect to theta. And then we can identify this bit here as theta dot. So this is times theta dot. So all of this here, this is my r dot. Okay. So that's nice information to know. Maybe we can make that a little bit more clean down here by saying here r dot is, now rearrange, theta dot e to the theta. Nice piece of information for us. All right, and we're going to perform a same sort of thing for r double dot. Okay, and so here r double dot is the time derivative of r dot, which is the time derivative of that expression that we just came up with, theta dot e hat theta. Again, I can sort of use my product rule on this. If I think about this as u and v, then you have u dv plus v du. That's my product rule in action here. And so we can get for ourselves something like the derivative of the first bit times the second bit plus the first bit times the derivative of the second bit. Okay. That's with my product rule. And then I can start to identify some of these things. All right. So d theta d dot dt, this is just theta double dot. E to the theta will remain sort of untouched. Theta dot, okay, well, this just is going to remain untouched. And then the derivative of e theta dt, well, I've already got that. That is dr dt, which is just what I found up here. So you can either label this as r dot, or you can sort of spell it out fully if you want, understanding that in the end, we're going to end up with something that looks like r double dot is equal to, I'll sort of take the first bit here, which is theta double dot e to the theta, that's this first term here, plus theta dot times r dot, which is theta dot theta. Or I could think about rearranging this by pulling out e to the theta. And you'll end up here with theta double dot plus theta dot squared. Interesting stuff. Okay. So now that we have expressions for r dot and r double dot in terms of things we know, so remember, we know theta double dot and theta single dot at a certain value of theta. So we can start to sort of figure out what's happening in this particular problem. So now let's use information we know. Right. So we were given information about theta. So theta is pi on 4. Theta dot is 2 radians per second. Theta double dot is 4 radians per second squared. So we'll recall that. Okay, so this is information we were given in the problem. And we can use that now to calculate the various values of r dot, and r double dot for this particular problem. So then we know that r is e to the theta. And at this particular snapshot in time, which is what we're interested in, we have e to the pi on 4. If you want this in decimal form, this is a known amount. This is 2.19 meters. You can just plug this into your calculator if you'd like. So also, we have this expression for r dot now, which we found previously, is sort of this theta dot e to the theta. At this particular snapshot in time, theta dot is 2 radians per second, and again, theta is still pi on 4. So we have here 2 radians per second, e to the pi on 4. This is going to get here this radial velocity, which is 4.38 meters per second. Finally, our sort of complicated equation that uses r double dot, remember, was something like e to the theta double dot plus theta dot squared. Here, this is e to the pi on 4 times theta double dot, which I was given at the very beginning of the problem, 4 radians per second squared, plus my angular velocity given was 2 radians per second squared. Okay. So put this all together, and we get an r double dot here, which is 17.52 meters per second squared. So at this point, we have all the information for this one particular snapshot, which is the very specific moment when theta is equal to pi on 4. So here I have my r double dot, here I have my r single dot, and here I have my value of r. And alongside of that, I have all the values of theta, theta dot, and theta double dot. So I'm finally ready to go back to my velocity and acceleration equations, plug everything in, and calculate the velocities and accelerations. So then I'm ready to finally answer the question and say that my velocity, which I know is r dot e hat r plus r theta dot e hat theta, at this one particular snapshot, so at this one particular location, theta is pi on 4 radians, you will have here this one specific point. We have this r dot value, which you've calculated as 4.38. You had r plus the value of r, which we calculated as 2.19. Sort of dropping my units here. Theta dot, which is 2 radians per second, e hat theta. And then on this entire thing, we will have meters per second. So the velocity at this one particular snapshot in time is going to be here 4.38 in the radial direction. So that means sort of in the direction of the unit vector that points along the position vector. Plus here, what is going to be 4.38 e hat theta. Interesting that we have equal contributions to the velocity vector in both directions. Just happened to sort of be by chance in this situation. So this would be my velocity vector in this problem. I could do a similar thing with the acceleration vector. Or remember acceleration given by r double dot plus r theta double dot. Oh, sorry, that's wrong expression there. Got my components mixed up. Minus r theta dot squared in the radial direction, plus my transverse terms, which are going to be here. Make sure I get this right. 2r dot theta dot, my Coriolis term, plus my transverse acceleration term, r theta dot, e hat theta. Okay, baby. All of these things, again, we have at this particular snapshot. So here, let's just plug everything in. R double dot calculated 17.52. Again, I'll drop my units, which is meters per second squared. We'll come back to that at the very end. Minus my position at this particular time, calculated 2.19. And my angular velocity at this time, just 2 radians per second squared. All this in e hat r. Plus 2 times my radial velocity, 4.38 meters per second, times my angular velocity, just 2 radians per second, plus my position at this time, 2.19, times my angular acceleration was 4 radians per second squared. All this in e hat theta. Run out of room there. So at this particular snapshot, the acceleration after plugging everything in and calculating this is going to be 8.76 e hat r plus 26.28 e hat theta. meters per second squared. And there's my acceleration vector at this particular point. All right. So that's how we go about these problems. A little bit of calculus tricks, a little bit of calculus techniques to sort of get you there with the weird time derivatives of an equation that happens to be a relationship between r and theta, which is a little bit strange. One last thing I want to do is I actually want to sketch kind of the acceleration and velocity vectors on this particular particle at this particular time. So let's go ahead and try to make a sketch of what's going on here. Okay, so here's my origin for this particular problem. Okay, if we go all the way back up to the picture, here we are with our particular picture. Here's our origin down here, and it's following, again, this sort of strange path, which is given by the equation r is equal to e to the theta. I'm asked for a very specific snapshot in time, and that snapshot is when theta is pi on 4, and I'm told information about what's going on at that particular time. So let's put our point P in here, and we'll draw acceleration and velocity vectors on that point and sort of see what's going on here. Okay, so at a 45-degree angle with the horizontal, let's say that this is my horizontal, I have my position vector, which locates my particle. So at 45 degrees, maybe my particle is here. That seems like as good as any spot for my particle P. So here's a position vector that locates particle P. Here we are with our position vector R. That angle that we've made here with the horizontal is pi on 4. Happens to be my angle of theta at this particular snapshot in time. We can put our unit vectors on here. So here's my unit vector E hat R. It's the unit vector which points in the radial direction. Then 90 degrees counterclockwise from that is E hat theta. It's the unit vector that points in the transverse direction, 90 degrees counterclockwise from E hat R. And let's see if we can do something about putting velocity vectors in here. We go back up to our velocity equation here, we see that we have equal contributions in both E hat R and E hat theta. So that means that my particle happens to be moving equally in r and theta at the same time. So I'd like to represent that with the vector that I ultimately draw for the velocity. And so if I'm thinking about this E hat R, E hat theta coordinate system, and I have equal contributions in both E hat R and E hat theta to the velocity, that's going to result in a velocity vector that is exactly pointing right in between those two vectors as best I can, with equal contribution in both directions. So it would sort of look like the velocity is perfectly vertical, considering this here is a 45-degree angle and this here is a 45-degree angle. So here the velocity, which is, I think it was 4.38. Yeah, 4.38. Okay, so there's my velocity vector. Now let's take a look at the acceleration vector. It's telling us how that velocity is going to change over the next time interval. And here we see that acceleration vector. This one's a little different. I have a bit of a stronger component in E hat theta than I do in E hat R, and it's about 3 to 1. So I would expect, you know, the E hat theta direction to sort of dominate the acceleration vector. So if I wanted to draw that in here, I want to bias towards E hat theta. Thinking about splitting that 90 degrees up into 4 segments and going 3/4 of the way from E hat R to E hat theta is probably the most appropriate. So my acceleration vector, yeah, let's do it in green. And I want to differentiate. Let's do it in black. So here my acceleration vector will look something like this. Okay. So much more of the component in E hat theta than in E hat R, as was given by our math that we went through. So here the acceleration, 8.76 E hat R. So if I sort of project it down here to the E hat R direction, I'd have that kind of amount in the E hat R direction, plus what is 26.28 in E hat theta meters per second squared. Okay, so a nice sketch of kind of what's happening with our particular particle here, showing us sort of our velocity vector, you know, where the particle is heading, and where that velocity vector tends to be moving. Now, if we think about our sort of picture, this all sort of makes sense, right? So remember that velocity is always going to be tangent to the path. And so if we go up to our picture here, we should see that the velocity is going to be roughly tangent to the path at that particular point. Okay. So if I thought about what is the 45, well, maybe this is the 45. I guess maybe this picture isn't perfectly accurate, but if we were right at the 45, we would expect this velocity vector to be pointing almost perfectly vertical. So that's probably more appropriate to locate where the particle would actually be, considering this picture is maybe not perfectly scaled. Right. So nice representation there. Okay, that's going to be it for this video. Thanks for watching. Hopefully it's helpful for your homework as you power through numbers 4 and 5. We will see you tomorrow for a normally scheduled lecture. Ta-ta.